Yo, what's up, guys? Welcome back. Um, as you can see, we got Linux on the system now. I was like pretty much customizing it like all day yesterday. Took a little while, like kind of installing everything that I need and figuring out alternatives and setting up some keyboard shortcuts and other things and just setting up the desktop environment and everything. So it definitely was a long day. But yeah, we got it all done. We had a few issues as well. I'm still, obviously it's going to take me months to learn the OS, but it's been pretty good so far. I really am enjoying it. Setting up some keyboard shortcuts. It's fun. Just setting up stuff, cool things. Opening terminals, whatever. But yeah. Still trying to learn the terminal. But it's been good so far, so I'm enjoying it. It's definitely a lot more smoother. But yeah, I do like everything. So yeah, it's been good so far. But anyway, we're gonna get into our problem of the day today. So let's take a look at Pokemon 111. I'm gonna Rhyhorn today. Rhyhorn sound. Let's take a look at the sound. There's our sound of the day. Ah, man. Need to crack my hands, but I can't. But yeah. So, let's take a look at a quote of the day. Oh my gosh, dude. This stuff is confusing. But yeah, let's take a look. Let's take a look at a motivational quote of the day. I'm still trying to figure out the OBS settings. So maybe if it looks weird or it's not 1080p or whatever, I guess I'll keep trying to figure that out. It's a little different with all the stuff, but we'll get it going soon. Get a quote going for today about success is getting what you want, happiness is wanting what you get. Let's go. Success is getting what you want, happiness is wanting what you get. By W.P. Kinsella. Not sure who this is. Canadian novelist. Died about 10 years ago. University of Victoria. University of Iowa. No way. Man, going from Iowa to... It's cool. Canadian novelist. Nice. That's cool. Anyway. Let's jump into our problem of the day. Let's take a look. I believe... God, more dominoes, but I guess since it's easy, we have to do it. Just jump on the J, find the dominoes you've already seen. Dominoes. Okay. Given a list of dominoes, dominoes I is equal to AB is equivalent to dominoes J. Given a list of dominoes, dominoes I is equal to AB. Dominoes J is equal to CD. And if and only if A is equal to C and B is equal to D, or A is equal to D and B is equal to C. That is, one domino can be rotated to be equal to another domino. Return the number of pairs ij for which 0 is less than I is less than j for dominoes dot length, and dominoes I is equivalent to dominoes j. Okay. Looking if A is equal to C, so it's not. B is equal to D, so it's not. Or A is equal to D and B is equal to C. That is, one domino can be rotated to equal to another domino. Return the number of pairs ij for which 0 is less than I is less than j. If dominoes are length, the dominoes I is equivalent to whatever. Okay. Let's do, okay. For I in range length nums. Alright, let's print out I. Let's see what we get. Should print each one here. What is it? Dominoes. Whoops. Dom in O's. Okay, we print each one. Right, so then we go, okay, well, for A, B in range length dominoes, let's print A, B. Cannot unpack non-iterable int object. What do you mean? I'm gonna sneeze, bro. Cannot unpack non-iterable object. What is going on here? So we want to. Okay, let's do I is equal to, sorry, A, B is equal to I. And then C, D is equal to J. But we start from I plus 1. Okay, so check if dom in O's A is equal to dom in, I'm gonna copy this, man, I hate this word, dominoes B. Let's put parentheses around this, okay. Then we have an or dominoes, sorry, dominoes A is equal to dominoes C. Dominoes B is equal to dominoes D. And I guess I is always going to be less than J technically, so I don't think we need to do that, but then we do output is equal to 1, so we would do count plus or equal to 1. Need some sort of count variable up here. And then we would return a count. Cannot unpack non-iterable int object. Why is it doing this? Oh, this is an int. Maybe it has to be dominoes I. Dominoes J. Maybe because that's the index, actually. Oh my god, bro. This index is out of range. Okay, maybe we have to do a do an and. 0 is less than or equal to I, but is less than or equal to 0. Less than J is less than the length of DOM in O's. Come and share with me our favorite song going on TV. Oh, we don't have to. Okay. Let's just full screen this. Why does this not like this? Why are we getting E index out of range here? Why are we getting list index out of range? Please tell me, because I am not sure. Telling you that somewhere you were doing Domino's X where X is not a valid index into the list. Ooh, is that because we have to do the... Maybe we have to do this first. Could that be a reason? We have to check the bounds first. No. So it's less than I, it's less than J, but it's less than... I'll re-index the list. What do you mean, bro? You're telling me I don't need this? I'm getting an index out of range, though, dude. What do you mean, bro? Oh. Wait, given a list is equivalent to Domino's J is equal to CD. Wait, given a list of Domino's I is equal to AV is equivalent to Domino's J is equal to CD. Apparently here we're just comparing the indice, bro. Is that what I messed up? No way, that's... make it equal to the values here. Expected 0. Output 0 got 1. A is equal to C and B is equal to D. A is equal to D. B is equal to C. There we go. Okay, I didn't think about that because these are technically, we're assigning the values here because of assigning Domino's I. So that's probably. Is it too slow then? Time limit exceeded. No way. You can keep track of what you've seen using a hash map. Okay. My dictionary is equal to hash map. What do we use as the key though? Oh my god, dude. So, well, A is going to go through each one. A. Trying to think here. How can we make this? How can we use a hash map here to hash table counting? But what we store though, if we store the key AB, how would we make in so using hash map? Does it accept the n squared solution, bro? Like, what? Bro, what? Bro, how do I get a TLE? But maybe if I do the length. Dom in. Bro, I hate the word dominoes, dude. Literally, like. Let's do, and maybe this will make it faster. I don't know. This is the only thing I could think of that could speed it up. I guess I initialize a dictionary. Nope. I guess you get a TLE in Python. Okay, anyway. This is the brute force solution. How do we think about the and squared solution. I don't know what the oven approach would be. See if I get some upvotes on that, maybe. I don't know. How can we do this? We can do AB. Maybe we can do for AB in range length in N. Let's print AB. Cannot unpack iterable, dude. What? So toxic, dude. We have to do in dominoes. Okay, there we go. For each domino j, find the number of dominoes you've already seen. Dominoes I with I less than j that are equivalent. So we have to normalize it apparently using key is equal to AB if A is less than or equal to B, else BA. Okay, and it's plus or equal to freak key plus or equal to 1. Should be count. So we go loop through, we get our key, we make our key if A is less than B, else BA, count plus or equal to freak key. Shouldn't it be freak key? Okay, if key not my dictionary. Let's do minus go dictionary key on count plus or equal to 1. Else free key plus or equal to 1. Free key plus or equal to 1. It's definitely gonna be wrong, bro, I think. Oh, whoops, we need got 4. Let's do count plus or equal to. I realized that we need. We don't just automatically count when we see one of them. We need at least 2 of them to count. We're gonna double the amount every time. I think we're gonna put this back here. There we go. Submit that. Oh my god. There we go. Okay. Oh, dominoes if string val and count. Okay. So if string val and count. Also string val. Also string val minus 1 on count. They're going in reverse. Also you want else count string val is equal to 1 if it's not there. For v and count values. Return as. Okay. We kind of do it dynamically in one hit. Interesting problem. I didn't really feel like I could have got the O-Van solution if I just don't want to. This one domino can be rotated equal to another domino. Return the number of pairs ij. Yeah. I feel like I could have got the O-Van solution, but it's alright. Let's do like a in order. Yeah, let's do like an in-order traversal. It's been a while since we've done one of these. We did it Feb 14th. Give the root binary tree, return the in-order traversal of its nodes. In-order traversal would be left, root, right. Because left's the smallest, the root is middle, and then everything higher than that is right. So it would be shit. It would be all the way to the left. We'd start here and go dun 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 dun. Right? 4, 2, 6, 5, 7, 1, 3, 9, 8. Could you do it iteratively? Okay. I feel like we have to go all the way left first, I think, right? Been a while since we've done a tree problem like this. Because we have to start from this value here, right? The only way to start from this value here is that if we keep going left, right? What the hell? So maybe we can do like a while root dot left val is equal to root. Root is equal to root dot left. Let's do val is equal to root, right? And then we can let's print out val. Okay. See if what that gets us. I think we gotta go all the way left first. Or it's not associated with a value. Val. Start at leftmost val. Leftmost node. Def. DFS, passing our node, right? We'll call that down here. Let's do our DFS node. We need, okay, we're returning some sort of list, so we need a list here. Okay, well, if we were to do node.left, maybe we don't need any of this, actually. right? Maybe we just started our left node, right? We could do, okay, well, if node.left and node.right, okay, wait, if not node.left and not node.right, we want to append a child, right? So we can do, okay, well, node, we can do res.append res.append node.val, right? If not node, if not node, we just want to return, right? Then we want to call left node, DFS, DFS node.left, DFS node.right. Right node. Otherwise, then we want to append the current node that we're at. Res.append. Wait, hang on. So we start here. We would come through here, if not node.left. So we keep going, we keep calling node.left, then we call node.left, right? We get here, and we'd see, okay, if not node.left and if not node.right, then we would append, right? Okay, we append this node. And we come back here. We go, we want to append this node, and then call node.right. So I think we would go here, append current node, right? So we would go res.append node.val, right? We want to append the current node before we go right, right? And then we would go right. Okay, so we go, well, if node.left, if there's a value there, let's go here. If node.right, well, maybe we don't even need this, bro, because technically we're checking that here. DFS node. Let's return our res. Node is not defined. Did you mean node? Oh, I meant root. Sorry. On 3, 3, 2, 1. We'd append 1, then we go node.right. We get to node.right, and we see that we have looks like we're accidentally appending nodes twice. We're getting the right value, but we're accidentally appending nodes twice. maybe we don't need this. I feel like we do. We do need this. Okay, let's try and walk through this. 1. Right, we start at 1. If not node, it is something. If not node dot left, we have something, right? Then we go to a left node, right? Go to left. If not node, we return, right? Then we come back here. We append 1, okay? Then we go DFS node dot right, and we would go right here, okay? So we go right. Then we see, okay, well, if not node, that's not true. If not node, that's not true. We go left, right? We go left. If not node, that's not true. If not node dot left and not node dot right, then we res dot append, right? So we would res dot append here. Ah, but it keeps going. That's why we need the return here. That's what we're missing. We're missing the return. Locked. Locked. Okay. Locked in, baby. Locked. Locked. Okay. Let's get rid of this. Let's try and do the stack solution. I feel like we haven't done a iterative solution in a little while. Stack is equal to this. We do while stack, right? We obviously need to append our first value, right? And our first value, what do we want to keep track of? We're going to want to keep track of the current node that we're looking at, right? So maybe we only need the root, right? Technically, because append root. Okay, so while stack, right? We can do, okay, well, I feel like the iterative solution is a little, okay, so we append to our stack, we append our root, we loop through with our while stack, right? And while stack, we want to check, need to get to our leftmost value, right? So I'm not sure actually. 94 binary tree in order traversal. Iterative using stack. Initialize an empty stack and set cur to be equal to the root. While either the stack is not empty or cur is not null, go left. Push cur until you hit null. Sorry, I forgot we need our res array too. While stack. While cur or stack, right? We loop through. We do while cur stack dot append cur. Cur is equal to cur dot left, right? We go all the way. Okay, we append all the values. Once we get to the left, okay, what do we want to do? We want to check, well, stack is for last in, first out, right? So we're looking at this value. We'd have to do, okay, well, node is equal to code.pop, okay? Probably want to append it to res.append node.val. Apparently we append node.write there. I remember doing this. The solution is a little trickier because we start a cur, we pretty much loop all the way down right to here, okay? Then we append node.write, okay? So we are at the leftmost file. We know we're at the leftmost file, right? Because it breaks out of this while. Then we go node.write. Sorry, we pop here, right? So this is our first value we look at. We append this to res. Then we do node.write. We see nothing is node.write. Then we come back. Then we cur is equal to node.write. Then we do while cur. There's nothing in cur, so we don't even append, right? So then we will go back to here, right? Node is equal to stack.pop, right? So we append this value, okay? And then we do node.write, okay? And then we do while. Then we go node.write here, okay? We probably would check. Then we'd go while cur is equal to node.write, we'd append this one, and then we'd do this first. Then we come back to this one. Do node.write, see there's nothing. Come back to this one, node.write, see there's nothing. Come back, append, and then append this one, append this one, append this one, append this one. Node.write. Then we try to go left, see there's nothing, right? Then we go node.write and try to go left, come back to this one. Yeah. Interesting solution. Okay. Let's jump into another problem. Reset my roadmap. I have to figure out what I did. All right, I think we did all of these. I think. Graph problems, man. Which ones have we done? I'd have to go through all this again. I know we did these two for this one. Heap priority queue. I think we did all of these. I think I'm gonna have to go through this on my own. Take a look. 1DP. I know we did most of these. I know we did this one the other day. We did word break. I think we did these. I think that's what it looked like. Graphs. I know we've done number of islands. I know we've done this one. We've done clone graph. Running oranges. I know we've done this one. I just wasn't sure. I know we've done this one. Let's check out some 2DP. Oh, 2DP is gonna be tough, man. Oh my god, dude. Oh. You need paths, dude. There's a robot on an M time zone grid. The robot is initially located at the top left corner, grid 0, 0. The robot tries to move the bottom right corner, i.e. grid n-1, n-1. The robot can only move either down or right at any time. Given the two integers m and n, return the number of possible unique paths that the robot can take to reach the bottom right corner. Holy shit. Okay. Number of unique paths. Would this be I'm thinking DFS here, the first thing that comes to my mind. Or could it be BFS? Or we can either go down or right, so we would go programming combinatorics, math. Okay, rows is equal to the length of m times n. Ooh, okay. I can see why. Okay, I can see why the I was rejected. Hey, just said it was complicated with high memory requirement. The interview also asked you pass through a second, which I solved it again using matrix, which uses m times n space. That's what I'm thinking about how to use it using a matrix, but okay, like we can do for I in range. Okay, for row in range length m. For col in range length col. Let's do grid is equal to grid row col is equal to 0. We just need to make a two-dimensional grid. Jeez, how do we do that? How to initialize? I don't think I've ever had to do that. Initial array in Python. What was list comprehension? a two-dimensional list using double for in Python. Let's do red is equal to this. Call is equal to, sorry, row dot append 0. Grid dot append row. Let's print out matrix. Oh, we want to print out grid. Whoops, grid. Has no length M in range M in range N. Okay, good. So created our grid. We've got zeros everywhere, right? We start at 0, 0. We can go down or right. Then from here we can go down or right. Okay. From here we can go down or right. From here we can go down or right. I feel like this can be solved using BFS. Like the memory would be like crazy high. Definitely pull TLE, but right, we can go either right, down or right, right? And we go either down or right, and we go down or right. We're gonna keep going until we get, I think. So I think then we can probably add some sort of dynamic programming from, I don't know. Let's just see, bro. Who knows? Okay, so we can go, I feel like we'd have to, from collections, import DQ, right? We can do, well, while queue, right? Let's create our queue. Let's do Q is equal to DQ. Okay, we obviously need to put in our starting position, right? So our starting position from here will be shit, man, what would be our starting position? Starting position would be 0, 0. So Q dot append for 0. How did we do it in the other ones? Rotting oranges, Leetcode. Where are my submissions? How do we? Row call 0. That's what we did. Okay. Okay, yeah. So we. Okay, so this is like. Let's move this. Let's get rid of this. Okay. Get rid of this. Okay. This is creating the two-dimensional grid, right? So now we need to loop through for row in range length. Let me make rows is equal to the length of, I guess we can just reference M here, but we'll just do this, the length of range M equal to the length of grid. Calls is equal to the length of grid 0, right? Range rows. For call and range calls. Okay, we want to do append grid, right? But really, when we start here. Okay, this is a valid point, right? The robot is initially located at the top left corner. The robot tries to move to the bottom right corner. The robot can only move either down or right at any time. Given the two integers M and N, return the number of possible unique paths that the robot can take to reach the bottom right corner. Okay, so we're not looking at each square. We're looking at starting at this square. Where can it go, right? So maybe we don't need this loop technically, no? Because we're not checking each different square. We're checking one specific square. So here, right, we go while q, right? We probably want to initialize our q. So q is equal to dq. And then we want to q dot append. We want to append our row, our call. What do they append? Row call. Okay, yeah, row and call, I guess. That's really all we need, I think. Would we need a visitor array? I think we might need a visitor array, or can we only go down and right? So really if you go right, down. Are we ever going to revisit, right? Are we ever going to go back? I don't think there's a way that we can ever go back, so I don't think we need a visitor array. I don't think it's possible if we can only go down and right. Tries to move the one right corner, robot can either move down or right at any point in time. I don't think it can go backwards. Yeah, so I don't think we need a visitor array. Add a note here, no visited, because it can only go right or down, right? Q.append. Really, we just need to append the starting value, right? Which would be 0, 0, right? So we go while q. Then we go, okay, q.pop. Sorry. Let's do row call is equal to q.pop left, right? We probably need a directions array as well now that I think about it. So directions is equal to, okay, we only need to go down and right. So to go down, we go 0, we increase, right? 1. To go right, we need to do a row. Right, to go right, our row would sorry, I think this would be the other way around. I think it'd be 1, 0, right? That would be to go down. And then to go right, have to use that column, which would be, I think, 0, 1, right? This goes down, right. Let's just confirm. I'm pretty confident. This go down and right. 2-dimensional grid. Okay, looks good. Okay, so we want to pop here, and then we want to check, okay, well, hold each of the directions, right? So from here we can either go right or left. Well, this. Can this be done using iterative DFS? I don't know. Now I'm starting to think maybe we have to do like a recursive DFS or something. Like, can 62 unique parts be solved like this using using iterative BFS with a queue? So this would be more of a brute force solution. Okay, so it would. Now that I think about it, the reason why I was a little concerned was because the iterative, technically we go here, we have two potential things, right? We append this one and we'd append this one. And then when we go here, we look at this one, we'd append this one and this one, right? And then when we go here, we'd append this one and this one, right? And then when we go here, now we're appending this one, this one. This one's appending this one and this one, and this one's appending this one. So it kind of makes sense, right? It'll do it, right? So now we go for CR current row for NR NC in directions, new row, new column in directions, right? We want to create, well, new row is equal to row plus NR, new col is equal to col plus NC. Then we want to do, okay, well, we need to check our bounds, right? So do our bounds. If new row, if 0 is less than or equal to new row, but is less than rows, right? And 0 is less than or equal to new col, but is less than cols, okay, then it's valid, right? Then we can do q.append new row, new col, okay? Okay, so then we check, well, if new row and if new row is equal to grid, well, I guess rows is technically 1, 2, 3, 4, 5, 6, 7. Cols is 3, right? 1, 2, 3, cols is 1, 2, 3, 4, 5, 6, 7, right? Grid is equal to rows minus 1 is equal to rows minus 1 and and new col is equal to cols minus 1. Right, is it cols? Yeah. Then we can increment our count by 1 and we can break, right? Break out of this loop. We didn't create a count variable, so let's make a count variable. Okay. If not, we would just append, right? Okay, let's return our count. See what that gives us. I think we need a... Let's go. We got the brute force solution. Goated. Obviously, it's not going to pass. I mean, it's... Oh. Maybe we need, like, well, if... m is equal to 1 and n is equal to 1, we return 1. Let's see what that does. I don't know if that's an edge case. Maybe it is. I have no idea, but... Okay, memory limit exceeded. Okay. Okay. So we get a memory limit exceeded here, right? This is the brute force solution. Now we have to figure out how we can speed this up. How can we speed this up? Something stuck in my ear, bro. Okay. Okay. Wait 1 second. I know yesterday, technically, I said I was going to do a recursive or a DFS graph solution. I feel like I had a long day tomorrow. I totally forgot I said that yesterday, so I just realized that now. I think we'll probably do that tomorrow. Dynamic programming O of n times n time O of n space. You know that to get to cell ij, you must have come from I minus 1 j or I j minus 1. So if you let dpij equal the number of ways to reach ij, then dpij is equal to dpi minus 1 j plus dpi j minus 1. one way straight along the top row, left column. dp is equal to unique paths. 0 times I guess in this case n is the cols, and sorry, n is the cols, m is the rows, right? Zero times n, right? So we would go, okay, let's take a look at this. So maybe we can do like some sort of oh my gosh, dude. Bless me. Right, we can make our directions array. Okay. Alright, maybe we can we technically go, well, thinking somehow we can use it with the directions array, but we don't have an array, so it says here they go for I in range 1 to m. Okay. I in range 1 to M, which is the rows. They go for J in range 1 to N. I guess they go, whoops, they go 1 times N, right? They skip 1 because at the first point at 0, 0, it's always 1, right? So then we go dpj plus or equal to dpj minus 1. Then we just simply return dp minus 1. What a simple solution. Wow. Didn't know it would get as simple as that, to be honest. Unique paths. Let's check out Leetcode's thing about it.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's look at unique paths. So this is a dynamic programming problem, and it's a relatively straightforward one compared to a lot of more difficult dynamic programming problems. We are given a m by n grid, and so the top left in the grid is always going to be our start value. And so from our start value, it's like a game. We have two choices no matter what position we're at. We can only move right or we can move down. Those are our only choices. We can't go diagonal, we can't go up, and we definitely can't go left. So our goal is to reach the end position or the finished position, and that's always going to be the bottom right. So we start at the top left, but we want to go to the bottom right. And the only question is, how many unique paths are there to get to the end position? So at first, this kind of seems like a recursive problem, right? So we have two choices, right? We can go down or we can go right, and then that's a sub problem. One thing to notice is, see how from this start position, we are actually able to move to any position in the entire grid. But if we move right from this position, what are the possible spots we can go to? Well, we can go right and we can go down, so we can actually go to any spot here. But notice we will never be able to reach these two elements if we start from here. And similarly, if we go down from here, then what positions can we reach? We can reach any position to the right or below, but we'll never be able to reach any of these positions. And another thing to notice is literally any spot in the entire grid, the nature of this grid, and since we can go down and we can go right, any spot in this grid will be able to reach our destination. So we don't have to worry about not being able to reach the destination. So yeah, you might try this problem recursively, right? So we have two decisions, go down or go right. And that's great, right? So now from here, we also have two choices, go down or go right. From here, we have two choices, go down or go right. You kind of notice though, there's some repeated work. Obviously, we can get to this position two different ways. So in that case, we're going to end up doing repeated work, right? From this way that we got here, we can go down and we can go right. And we're going to repeat that over here, right? Go down or go right. So if we're doing depth first search recursively, one thing we can do is have a cache. So for every row, column, position. So for example, in this position, we cache the result. So if we ever reach this spot multiple times, we will be able to store that and we won't have to run depth first search again because depth first search is pretty expensive. And so what is this value even going to store? Well, this is recursive. So for each position, we're actually calculating the number of ways we can reach the destination, right? And if we can compute that for every single square, then we can compute that for the original square, right? Basically what I'm saying is the result that we're looking for is actually equal. So let's say we call this spot R, we call this spot down, right? So this is R for right, this is D for down. the result that we're looking for is actually the sum of R plus D, right? But then you might ask, well, how do we compute R and how do we compute D? Well, R is just going to be, R has a value to the right of it and it has a value below it, right? So if we want to compute this value, we can just take the right and down values and get them, right? But so what ends up being the base case? So with all that in mind, what ends up actually being the base case? Well, so this is the ending position, right? So how many ways from the ending position are there? How many unique paths are there to get to itself? Well, we can choose to define that as 1. So if we've defined that value as 1, we'll notice that things actually work out pretty nicely, because let's take a look at this cell, right? We want to take the bottom value and the right value and then add them up, and then that's what we're going to put in this spot. But we see that there's nothing below it, right? That's out of bounds. What we can say is, well, we'll just define that to be 0, right? We'll define every value out of bounds to be 0. So if we ever need them, we can just say that they're 0. So then what becomes the value that we place in this cell? Well, we can take the right value, which is 1, and the bottom value, which is 0, add them together, and then we get 1. So we can just put a 1 over here, right? And you might notice, well, what if we want to compute the value in this position? Well, the exact same thing will take place, right? The value below is 0, the value to the right is 1. So we can say that there's one way from this position to reach the end result. And now what actually is that path? Well, we can't move down, right? That's out of bounds. So we can only choose to move right, and then we'll be able to get to the result. And you can see that's true for every position in the bottom row. So we're just going to fill these to be 1. And you might be able to see how we are going to arrive at the dynamic programming solution now. So the first thing for us to do is to compute this bottom row. Now let's start doing the next row, right? Because our ultimate goal is to be able to do this value. We can work our way from the bottom to the left, and then from here to the left, and then keep doing that, and eventually we'll arrive at the result. So what about this position? Well, it has a 0 to the right of it because the right is out of bounds. It has a 1 below it, so we'll take 0 plus 1. Again, we get 1. Now, what about this spot? This spot actually has a value below it and a value to the right of it, and those values are 1 and 1 respectively, so the sum is going to be 2. And that makes sense, right? Because if you start here, there's one path going to the right and then going down, right? That's one path to get to the result. And there's another path going down and going right that lets us get to the result. So it makes sense that this would be 2 unique paths to get to the result. And from here on out, it's basic addition, right? So down is 1, right is 2. Add those together, we get 3. Here we get 1 plus 3, that's going to be 4. Add this together with this, that's going to be 5. Add these two together, that's going to be 6. Add these two together, that's going to be 7. And so you notice now we have filled in the second row. It looks a little bit different than the first row, right? The bottom was all 1s. And now the only thing for us to do is to get this last row. So we look down and we look right. That's 1 plus 0. So we're going to get a 1. Notice how the entire first column is 1. That's actually always going to be true, right? Because think about it. From any position in the rightmost column, the only decision we can do is move down. So there's only going to be one path to the result. So this is going to be 2 plus 1. This is going to be 3 plus 3. This is going to be 4 plus 6. This is going to be 5 plus 10. This is going to be 6 plus 15. And so finally, we are at our start position. So we can take the bottom and right values, 7 plus 21, add them together, we get 28. So that tells us if we start here, there are 28 different paths we can use to get to the result. 28 unique paths. And when you look at the picture, it actually looks more like a math problem than a coding problem, right? And that's because it is. You can actually calculate the number of ways from the top left, I think, in constant time if you have like a math equation, but I don't know a ton about it. I'm just going to stick to the dynamic program. programming solution. So let's do what we just did in the picture. So I'm going to have a row, and this is initially going to be the bottom row. It's going to be the length of the number of rows that we have, which is n. But since it's a grid, you could probably use either m or n. And so since we know the bottom row is going to be all ones, we can start going through the other rows. So we can go through all of the other rows except for the last one, so m-1. And for each row, we're going to compute a new row. So this new row is going to be above the old row. And so it's going to be the same dimensions, of course. We'll initialize it to all ones. And to avoid the edge case of having to check out of bounds, what I'm going to do is go through every position, every column except the rightmost column. And we can do that like this because we know the rightmost column or the last value in every single row is always going to be 1, right? I showed that in the drawing. And so we're going to start at the second to last position, keep going until we get to the beginning and go in reverse order. So we're going from right to left. And we know that the new row, so if we're computing new row of j, it's going to be new row of j plus 1. So this is the right value, and the value below is just going to be the old row at index j. And so with this loop, we'll be able to compute the new row. And so after we do that, we can update the row. So the old row is now going to be set to the new row. And so it's going to keep doing that until we end up getting the last, or rather the first row, the top row that we actually want to compute. So after this has been executed, that's what's going to happen. And what we actually want to return though is in that first row, which will be in this variable, we want the first value. So at index 0, that's what we're going to return. So now we can run our code. And by the way, so it is pretty efficient because we did this in O of n times n time, and the memory complexity is just big O of n because that's the length of a row. So I hope this was helpful.
This is a practical and beginner-friendly course to build an
Take a look at, I'm going to study this DFS problem really quick. Nice. Okay. Here we create, looks like a hash map. Def DFS, right? It gives us a row and call. Okay. We start, we want to return DFS 0, 0, right? Start from the beginning value. Okay. We want to go to this value and go to this value, right? So if r is equal to n-1, okay, this is base case, right? This is what I was thinking too in the video to get to the end. n-1, 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 right? So, okay, we do, well, if row is equal to n-1 and call is equal to n-1, we return 1, right? Otherwise, if RC in DP, if RC in DP, then we want to return DP RC. Okay. Otherwise, we want to compute that, so we'd probably call DFS, right? If R is less than 0, or R is equal to M, or C is less than 0, or C is equal to N, we return 0. Okay, so then we need to do the bounds. Okay, so if R is less than 0, or R is equal to M, or C is less than 0, or C is equal to N, we return 0, right? Otherwise, call DFS function, right? We would do, okay, DP RC is equal to DFS DFS row plus 1, DFS row plus 1 call, or is it or plus DFS call, sorry, DFS row call plus 1, alright, and we return 0. Oops, row call. We got another row call. Oh, we got another one here. Row call row. I think we got everything. Unsupported operand times for plus. I'm gonna return TP row call row call. I like this problem better, and this is definitely the way I would have solved it. This is the dynamic programming solution. Right? So we go row is equal to 1 times n, okay? We go for I in range n minus 1. And minus 1 would be 2, right? So we want to start here, okay? Then we go for j in range n minus 2, because n minus 2 would be here. We start at n minus 2. We go backwards, minus 1, okay? We do new row. Oh, we forgot something in here, actually. Whoops. Let's do new row is equal to 1 times n. okay, new row j is equal to new row j plus 1 plus the row inside of it. We can only go down, right? Okay. And then row is equal to new row. Then we would return row 0. It's a good problem. But yeah. Okay, we're gonna leave it at that. I've been going for a little bit. I gotta get some stuff. Gonna go play pickleball this afternoon. So appreciate you guys watching, and I will see you tomorrow.